Imagine being at the most isolated point on Earth. No cell tower, no Wi-Fi network. But when you lift your head to the sky, there are hundreds of small satellites working above you. And with an antenna the size of a pizza box in your hand, you can instantly stream a series on Netflix, make a video call, or play online games. It sounds like science fiction, but it is real. The internet has become the oxygen of the modern world. SpaceX's Starlink project aims to deliver that oxygen not only to city centers, but to the middle of the ocean, the top of a mountain, and even the polar regions. And it does this with small satellites moving through the sky at 27,000 kilometers per hour. Starlink's biggest difference is that it buries the sluggishness of classic satellite internet in history. Because this system does not only receive signals, it can send and receive data at the same time. And it does this with the smart antenna on your roof called Dishy McFlatface. So how is this magical connection established? How are the satellites positioned in the sky? Or how do the antennas track these satellites? And how can this entire system transmit massive amounts of data in seconds at speeds close to the speed of light? So, as I explained in the previous video, wasn't the internet actually supposed to be carried through cables? Now come with me, and let us discover the science behind Starlink together. Today, even if you see nothing with the naked eye when you look at the sky, there is actually a dizzying crowd up there. Around 5,000 satellites are constantly orbiting Earth. From communication to navigation, from weather forecasting to Earth observation, they handle many tasks. In other words, we have built an incredible network not only on the ground, but in the sky as well. So how do these satellites keep orbiting in space without falling? The secret is actually hidden in two very familiar forces: gravity and centrifugal force. While gravity tries to pull satellites toward Earth, their orbital speed throws them outward. If those two forces balance perfectly, the satellite begins circling Earth in a stable orbit. It neither gets too close nor too far away. A delicate balance, a true dance in space. But there is also this. For a satellite to begin that dance, it must be launched into orbit at a very precise speed. Satellites in lower orbits have to move faster to resist Earth's stronger gravity. Fortunately, there is no air, friction, or braking in space. So once launched at the correct speed, they can continue moving along the same path forever without slowing down. Satellites orbit at different altitudes depending on their missions. These are generally divided into three main layers. The first is LEO, meaning low Earth orbit, the layer closest to Earth. It lies at approximately 160 to 2,000 kilometers in altitude. Satellites here can complete a full orbit around Earth in just 90 minutes. In other words, they pass overhead again every hour and a half. But because their coverage area is relatively small, if you want global connectivity, you need hundreds or even thousands of satellites. That is exactly why Starlink chose this orbit. The second is MEO, meaning medium Earth orbit, the layer above LEO. Navigation systems like GPS are located here. These satellites orbit at around 20,000 kilometers and can circle Earth once every 12 hours. So the position it gives in the morning can come again from the same point in the evening. The third layer is GEO, meaning geosynchronous orbit. This lies exactly 35,786 kilometers above Earth. The most interesting part of this altitude is this. Satellites here match Earth's rotational speed perfectly, so they appear fixed at one point in the sky. For that reason, They are ideal for television broadcasting and communication systems. Once you align your antenna, you do not even need to change its direction again. But not everything is so simple. There are regions in these orbits that require caution. For example, the Van Allen belt. This region is filled with high-energy particles and is a complete nightmare for electronic systems. When they strike a satellite, they can damage circuits or make them completely unusable. That is why satellites pass through this area very quickly, or avoid it entirely if possible. And finally, one small information bomb. The orbit called geosynchronous is so crowded that space traffic there is almost like rush hour traffic in New York. The International Telecommunication Union is responsible for regulating this traffic. Because every satellite is given its own parking space. Otherwise, terrestrial broadcasts could interfere with one another. So if you ask what Starlink's real story is, everything begins with tiny but super fast satellites silently moving through the sky. These satellites are only 550 kilometers above Earth. In other words, they orbit far closer than traditional television satellites, and they are definitely not slow. They glide at exactly 27,000 kilometers per hour, dozens of times faster than a bullet, yet silent and steady. Being this close has a huge advantage. Latency is almost non-existent. So, while playing online games, you do not get eliminated because of lag. Video calls do not freeze. Videos flow smoothly, exactly as they should. So, what does that pizza box-sized device providing the connection, Dishy McFlatface, actually do? Dishy is not an ordinary antenna. Like classic television antennas, it does not simply rise. Each of these antennas is controlled by microchips vibrating billions of times per second. The electromagnetic waves produced are sent into space like invisible beams, like the beam of a flashlight fixed on one point in the dark. But this beam is targeting a satellite 550 kilometers away, and those beams do not stay still either. Starlink satellites move so quickly, Dishy has to constantly redirect the beam, but not with motors. By changing the phases of the antennas inside a completely motionless device, it can steer the signal in different directions. In other words, it behaves like a hidden radar. This technology is called phased array steering. Since satellites leave its field of view every minute, Dishy constantly switches to another satellite. But you never feel that handoff. Everything happens in the background within milliseconds. The data transmission system used to create such a clear connection is also highly impressive. Starlink uses a modulation method called 64QAM. So what does that mean? Each piece of data is converted into different signal combinations and transmitted. Every symbol is sent in about 1/1000th of a second. It can carry 540 million bits of data per second. That means something happens thousands of times faster than a human blink. And Dishy spends about 93% of its time receiving data and 7% sending it. So if you are watching a series or a YouTube video, data is generally flowing toward you. This data is compressed first. Then it is sent from Starlink satellites to the ground at speeds close to light speed. The phased array antennas on Dishy instantly capture and decode those signals. Let me give you one more small but impressive detail. These signals have a wavelength of around 2.5 centimeters. That means for one signal to travel from Dishy to the satellites, there is a distance equal to about 22 million wavelengths in between, and that journey takes only 2 milliseconds. Of course, while all of this is happening, Starlink satellites are not idle either. Each one can communicate with multiple dishes at the same time. And not only with users, but also with ground stations through phased array antennas, like every instrument in an orchestra working in harmony. Since every antenna is designed to detect specific frequencies, outside effects such as mobile phone signals, sunlight, or radio interference can be filtered out. That keeps the connection clean and reliable. By the way, there are motors inside Dishy, but they are active only during the first installation. After setup, all steering is done electronically through phase shifting. That means no mechanical wear occurs inside the device. The system lasts longer and works with greater precision. In other words, nearly every part of this system works with clockwork perfection. The fact that a small antenna on your roof can communicate this clearly and this quickly with a satellite racing 500 kilometers above the sky is truly one of the engineering marvels of the modern age. To understand the difference better, let us briefly look at other satellites as well. At their core are devices called transponders. These receive incoming signals, change their frequency, clean the noise, amplify them, and send them back. Since these processes require a great deal of energy, satellites carry solar panels, and when the sun sets, batteries take over. Thanks to sun sensors that adjust the direction of the panels, the charge never runs out even in space. Every satellite is equipped according to its mission. GPS satellites, for example, carry tiny but ultra-precise atomic clocks. Thanks to these clocks, our positions can be calculated with meter-level precision. Earth observation satellites, on the other hand, are like spies in the sky, constantly taking images and rapidly analyzing the atmosphere. And Starlink, it is on a completely different level. Phased array antennas, beam steering systems, advanced modulation techniques may sound complicated, but the basic idea is simple. To deliver high-speed, low-latency internet even to the most remote corners of the world. Everything sounds great, but space is nowhere near as stable as we imagine. For example, temperature differences can vary at extreme levels. Imagine it jumping from -150 degrees to +200 degrees. That is why satellites are wrapped in dazzling gold-colored insulation foils. This is not just aesthetic, it is literally survival armor. Satellites also have to remain balanced like space ballerinas. Because they are affected not only by gravity or centrifugal force, but also by Earth's uneven mass distribution, the Moon's subtle pull, and even radiation coming from the Sun. So over time, they can drift slightly from their paths. That is where thrusters come in. These small but vital engines both place satellites into the correct orbit and skillfully help them avoid fast-approaching space debris. These engines draw their fuel from tanks inside the body. So what happens when the fuel runs out? That is when the time comes to gracefully leave the stage. Satellites that complete their missions are not simply abandoned, because if left uncontrolled, they could collide with other active satellites or spacecraft. That is why they are moved into a safe zone slightly above geostationary orbit called the graveyard orbit. Usually, about 3 months of fuel is reserved for this maneuver. In other words, even their farewell is written in advance. When humanity is finished with them, they silently drift into the darkness of infinity and gently exit the stage, never to return. Starlink, however, follows a different path in this regard. For these satellites orbiting in low Earth orbit at around 550 kilometers, moving to a graveyard orbit is not an option. Instead, when their missions end or problems occur, they slow down using ion thrusters built into their bodies. Thanks to this maneuver, they leave orbit in a controlled way and burn up as they re-enter the atmosphere. In the end, Those silent but constantly rotating metal boxes above us are working in almost every area of our lives. From the internet to navigation, from television broadcasts to weather forecasts, all of them continue their duties in the darkness of space with millimeter-level precision. And Starlink, especially in places without internet infrastructure, in villages, on mountaintops, and even on the open sea, makes being online possible. Imagine it. In a region where even letters once struggled to arrive, you can now download films on Netflix. Starlink may truly mean that geography is no longer destiny. Maybe the next time we look at the sky, we should listen not only to the stars, but also to the silent presence of the satellites endlessly circling there for us. Because they are humanity's quietest witnesses, watching everything we do in full clarity.